Okay, so I thought I'd point out a couple of things on these first two questions. This is definitely this kind of stuff is going to appear on the final exam. Final is Tuesday morning, bright and early. In this room. Okay, so on the first problem, you had a step up like this, where the height of the step is V0. And we studied in detail the problem where the energy is above the barrier. But this problem, I wanted you to be able to work what happens if the energy is less than the step height. Okay, so in this case here, the energy is above the potential on the left side, but below the potential on the right side. Where the energy is above the potential, you get complex exponentials, oscillatory solutions. When the energy is below the potential, you get real exponentials. So, so writing down the equation for on this side, time independent Schrodinger equation looks like this. And so you get complex exponentials because you have a negative constant here, the energy is positive. And so in each of the oscillatory functions, the trig functions, when you take the second derivative, you get a negative. And so the solutions in this first region are this form. An incoming and a reflected part. And K, I'm looking to specify what K is in relation to E. K is given by this relation, which you would get by substituting into this equation. That K has to satisfy this relationship with E. Or in other words, K is equal to 2m E over h bar squared. Okay, so that much I think everybody got. But in the second region, now, if I bring this potential over to the left-hand side like this, we have a different situation. Because this is negative. Energy is less than the barrier height. So you don't get complex exponentials, you get real exponentials. So the general form would be, discuss this here, h bar squared kappa squared over 2m is equal to V0 minus E. Okay, so you get real exponentials rather than complex. For kappa then is 2m over h bar squared V0 minus E all to the 1/2. So the wave function is oscillatory in this region. It's going to be exponential in this region, but if this term can't be permitted because it will grow exponentially in this direction, right? This is in region 1 and in region 2. In region 2 goes all the way out to positive infinity. This would blow up exponentially, and there's no way to normalize the probability. Total probability would be divergent. Can't make it 1. So you exclude that term, leaving only this term. Okay, and so there were bits and pieces kind of missing from, pretty common, not quite understand this. I did throw you a little bit of a curve, but you should be able to figure it out. Okay, now the final thing is the current in the two regions has to be the same. Probability current. This is not on the exam. So I just wanted, there were a couple of people trying to figure this out, but I wanted to point out how it works. So the current here, you see why the current has to be? Because the current's coming in, the net current has to be the same passing through this interface. And one-dimensional problems, remember there's this relationship between the current and the probability density. And if the probability density is not changing, that means the current has to be uniform all the way across. Okay. So the current if you evaluate the current for this wave function, you get h bar k over m times a squared minus v squared. That was a homework problem. We did that. Find the current and for mixed plane wave, right and left travel plane wave. We also did a homework problem where you looked at the current from a real exponential. When you plug this into the relationship, okay, so it's psi star d psi of dx minus psi d psi star dx. Minus, I think it's minus I h bar over 2m. I'm never really sure about this. I have to think about constants there.
I think the I is the I not. Oh, wait, never mind. I thought the I would be in the denominator multiplied by I over I.
No, that looks correct. Right. Okay, so if you substitute this wave function into there, this is what you get. If you substitute this wave function into here, you get 0. The real exponential carries no current, no probability current. So the wave function is decaying exponentially into this region, but there's no current flowing through it. So that means the current on the left, the current has to be uniform, so that means there's no current coming, no net current on the right side. So this is also 0. In other words, the conservation of probability in this case reads like this. I'm sorry, C is not equal to 0. Excuse me, that's not correct. That's not correct. I'll write that down. That's the conservation of probability. It says everything bounces back. The reflection probability is 100%. Nothing can make it into an infinitely wide potential barrier. So it's got to all come back. Okay, so there were a couple people who were trying to figure this out. So I want to point that out. That wasn't part of what I asked you. You understand this? What I got this? The simple harmonic oscillator, the second one. Yeah, let's see. I think do it one more time. I noted some confusion on the idea of direct substitution. So let's go over this briefly here. Oscillator in Hamiltonian looks like this. Equation looks like that. And you look at, you're given a guess. And you are to determine whether this can satisfy this equation. So if this guess is to work, you're going to find some constraint on alpha and also on E. So practice on taking derivatives of the Gaussian like this. Common mistake. Okay, so be sure you can do that without mistake. If I put something like x times this Gaussian, you can still manage to do the second derivative and so forth. Okay, practice that until you get it down. There are lots of websites you can go to practice derivatives. So if you need a suggestion, let me know. Okay, so we substitute this back into this equation. Times the second derivative. Okay, you're not done. So some people correctly noted that they could cancel the exponential everywhere because it's not zero. Write down an equation like this. Cancel it out here. Minus 2h bar squared and alpha squared x squared plus 1/2 x squared. And we leave it like this. That's where they would end. But this equation makes no sense. They would say they found E. E is a constant. It can't depend on x. If E is to be a constant, the right-hand side has to have no x dependence. You see why? This is a parabola, generically a parabola, a constant with a x squared. It means all of this must vanish in order for E to be a constant. So let's set this to 0. Coefficient, in other words, the coefficient of x squared has to vanish. So that gives us alpha. I think I've done this all correctly. But yeah, that's right. So alpha is then square root of km over 2h bar. Okay, so this will be a solution to this equation only if alpha is equal to that. If it's not equal to that, then it's not a solution. See the logic? Okay. So we've made this term go away, but now that tells us what E has to be. E is then h bar squared over m times alpha. H bar times square root of k over m. You should recognize the square root of k over m is the frequency of the classical harmonic oscillator, what we call omega naught. So the energy associated with that solution, the eigenvalue associated with that solution is 1/2 h bar omega, which corresponds to the ground state. The spectrum of the solutions, you should remember this. But you need to also remember what are the allowed values of the quantum number. So this would correspond, this wave function would correspond to the n equals 0. So the ground state. Okay. And I'm guaranteeing there's going to be something like this on the final, not least because there were a few people made mistakes on this exam. So get it down where you understand the logic of this. The idea is this is a differential equation. So the equation has, it's a function of x. And so you have to, the left-hand side has to equal the right-hand side as functions of x. E cannot be a function of x, it's a constant. So therefore the right-hand side also has to be constant. If you have any kind of confusion about why that is, now's a good time to get it down and contact me if you have still a question in your mind. Okay, any questions about those two problems? Okay, so the rest of the practice tests, it's pretty long. The real exam's not going to be that long. But I got lots of stuff on here for you to study. So what do you want to do? Just take questions. Can you go over numbers such and such, or do you want me to go through it? Well, don't have a lot of time, so it's a pretty long exam. So only got about a half hour. So I don't know.
Would you go through some of them and post a solution online so we know that what we're doing is right?
No, I'm not going to post the solution. We've had this on previous exams, and we've had lots of homework, and I'll do it right here, and I'll answer a question by email, but I'm not going to post the solution. I'm trying to get you to do some work, so it'll help you remember. Will help.
But if we do the work wrong, then we're screwed.
Send me an email and ask me if this is correct. Okay, how about that?
Okay.
I have a concept question.
Okay. Is it, let's stick with practice. And
I guess, yes.
practice exam, anybody got questions from the practice today? It should all be very familiar. Like I say, I think it's all appeared on previous tests, homework. be a table of integrals.
It's on Canvas.
Yeah, it's on camera. There will be a table of integrals. There were some occasional mistakes on the operator algebra. We were supposed to find, I think it was x and p squared. Or p. So there's no need to make this complicated. It is really pretty simple to derive this. Well, I'm using the commutator relation that x to p is pi h. Write it down this way. So if I have an x to the left of the p, I can move it to the right, but then I gain this extra constant. So here x is to the left of p squared, so you have to push it through twice. Okay, so xp then is I h bar plus p xp, oops, px, and there's still a p over here on the right. Okay, so now you've succeeded in getting x halfway there. Push it through the last p. Write it this way. And then you can substitute that for this. So we have two max left. And then this ppx cancels with ppx. Okay. So this is easy if you just keep your wits about you and just do it symbolically without, if some people wanted to go back to the way that we prove this fundamental relation by remembering what the form of the momentum operator is, derivative. So they wanted to do this problem that same way by making this a second derivative, then you can do it that way. But it's going to be easier if you just treat it symbolically, manipulating the symbols and figuring out I have to push this x to the other side of this p squared. And just do it that way. Okay, other questions on the practice exam?
Great, so I had a question. If you have the first scattering program, do you have a step down
Yeah.
from no potential to a negative potential?
Okay, that's a good one. That might be a good.
Does it
Problem for the
scattering
final.
notch? That's basically.
Say again? Okay, so this is the one you have in mind?
And then the x-axis would be the upper.
Oh, was that not the one that was covered in our practice exam, right?
It might be.
That might be.
Because that's what I remember I was arguing. I was trying to figure out, okay, when you say step down, do you mean go from 0 to negative potential, or do you mean going from a potential down to 0?
Doesn't matter.
Okay.
Right, it's the relationship, it's the difference between the energy and whatever it is that determines the way that. So what's important is this difference. So if you're marking 0 here, it's the energy from this, or if you're marking 0 down here, then but it's still the energy in relation to what it is local that determines whether it's a complex exponential or a real exponential or whatever it is. So you could set the 0 of energy anywhere, any way you like. So, but I would probably tell you, set it equal to 0 on the left, and then equal to a negative value on the right. Is that one of the problems?
Or,
Yeah. Look at the study guide.
I don't see it here on the.
The study guide for chapter,
Oh, the study guide.
for chapters following, for the test following chapters 3 and 4.
Okay. So let's just sketch how this would work. Okay, and I wrote it this way to make sure that everybody understands this is a negative number, right? Okay, so again, let's follow through. This is region 1, this is region 2. Let's mark E from this, from that point there. So E is above this. Can't be below this because there'd be no way to get it in. If it started off at infinity to the left, it would never make it in if it's below. Die off exponentially. Okay, so there's this. So again, we have the same form. Let's label it K1. We have the relationship that the energy is equal to h bar squared K1 squared over 2n. We get this by plugging this into this. So it's complex exponential, oscillate. Now on the step down over here, yeah.
Sorry, did you purposely leave out B, or is that just?
Oh, no, I didn't. Not on purpose. Thank you. Thank you. Okay, now in this region, what's it going to look like? I'll look that way to just to absolutely indicate this is a negative number here. So if we bring this over onto the right-hand side, this is positive. This is negative, just like over here. This is positive, this is negative, so it's still going to be complex exponentials. Okay. We would have h bar squared k2 squared over 2m is equal to e plus. Okay, similar to this, except it's with the wave number is changing when it goes into this region. Okay, so you can solve for K2, but we're only going to have one of these terms. This would be the general solution in here, but because of the scattering problem is set up with stuff coming in from the left, one of these terms is going to drop out. Which one? The left traveling, because there's nothing to start but the wave traveling to the left. There would have to be some other thing over here that is bouncing off of, and we're saying there isn't. Okay. Yes, ma'am.
For the first, first region.
Yeah.
I'm guessing confused because I thought you get like the B part when it's reflecting off, so I was just wondering when you get that.
Yeah, there is a reflection. Well, that's surprising. So let's just pursue that a little bit. So we write down the condition that the wave function is continuous and the source derivative is continuous. So we get over here A plus B is equal to C. And then we get I K1 A minus B equal to minus, I'm sorry, I K2 B. So the i's cancel in this case. But notice there's a different K. K is different in region 1 than in region 2. The wave number changes when it goes over that step. So you solve this for B and C. Do it here quickly enough, but you will get that there is actually reflection off a step down. Classically, you would expect none to come be reflected off a step down. You would expect all the particles just to speed up and they go over this step down. They would all speed up. Quantum mechanically, we get some reflection. So let's let's try that. I guess we could, let's solve for B, so let's eliminate C. Okay, so we have K1 minus K2. K1 plus K2. So B. The reflection coefficient was the ratio of B to A. Reflection probability squared this. So you actually get some reflection, depending on the difference between these two wave numbers. And they differ because there's a V naught over there and there's not here. Okay. Surprising result. That's the prediction of the Schrodinger equation. Get some reflection off of a step down. So what must be happening is the guiding wave structure is what's not taken into account by this energy diagram is the influence of the guiding wave structure. The guiding wave structure is altered by the presence of the step down, and there's some amount of the particles that get reflected off of the guiding wave structure.
So the guiding wave itself is altered. You're saying
Sure.
it's change.
Yes.
Into region 2. So the guiding wave structure in region 2 is different. Should be different from one in region 1.
Yes.
Because we're seeing different like reflections and transition. Oh wow.
Okay, so that would be an interesting problem to try. So you have to actually work the problem. Don't just remember. That's the problem with giving you questions that are kind of familiar. Is you think you already know it and you just start regurgitating. Don't do that. Actually work the problem out. So you have to practice that, so that when it comes time to do it on the final, that's not a foreign thing to do, right? Just to go back and work it out again. It's just something you have to have done enough times that you know what to do. But don't start making assumptions about things. Actually prove them. The other thing is here, the current is going to be the same, right? There's going to be a current in region 1, which is going to be K1 A squared B squared. And current in region 2 is going to be K2. And these have to equal each other, because there's no buildup of probability. It just flows through. Some of it reflects. But these two, the current in the two regions have to match. So notice that we don't have A squared plus B squared equals C squared. There's this K that's different in the two regions. So these have to equal each other. So this solution that we're getting for B and C from here will have to be such that this current is equal to this current. That's the conservation of probability. The current is the same. Okay, more questions? Yeah.
So does that mean like some of the members of the ensemble, they actually, when they enter region 2, if they reflect back,
They may not actually get to region 2.
oh yeah,
But they're reflected by something in this something relating to the step down.
does that mean its total energy would have been less? That must mean the total energy must have been less than when it's in. If it does reach region 2, it means its total energy is less than the potential.
The total potential. You could associate a potential energy with the guiding wave structure. The total potential energy would be the guiding wave plus this. But we haven't been dealing with the potential energy in terms of the guiding wave structure. We just think generically that there's some kind of force that the guiding wave can exert on the particle. So there would be some accumulation of force to the left so that some of the particles get reflected. But the Schrodinger equation explicitly deals only with the external potential, not the guiding. It's not present explicitly in the Schrodinger equation.
And will it ever be?
No, that's not the Schrodinger equation. If we have the guiding wave explicitly, it's a different equation. Schrodinger equation describes statistically the effect of the guiding wave on the particle. Questions? You want to pick one and try it? Shall we do that?
A question?
Yeah,
11.
11.
I know it's simple, but
Okay, that's a simple
it's
one.
been a while.
Number 11, is an atom changeable? What do you think? An atom is not changeable. Can you think of a change that can occur to an atom?
You can't swap out pieces and parts.
Right. Can you pull an electron off of the proton? You can destroy the hydrogen atom. Or you could excite the hydrogen atom so that the wave function, the particle is in the ground state, but it gets excited to a higher level, higher lying state, absorbing light, or it could emit light and make a transition to a lower state. So hydrogen atom is changeable. That's how we know about them. It's because we can see them change.
Is it also, did you say like it changes place and
It changes place.
changes not just like substantial change, but accidental?
Sure, can change place. It's pretty simple. There are not a lot of ways that hydrogen atom can change, but they're so it's pretty simple that way. But it is changing. In fact, I think he makes this point in chapter 1, or chapter 2. Other people talk about, was it Lucretius? Who is the guy, the Greek guy? Or Democritus? Who is it? I've forgotten who it is. They say he's the one who came up with atoms. Democritus. That's not, he did not have that concept at all. Democritus was looking for something unchangeable. And that things would be composed of these things that would be stuck together, but the things themselves did not change. So they're just kind of piled together like in a pile of marbles or something. That's not what we have. Atoms are changeable. So he didn't really conceive of atoms as we talk about atoms today, even though it's often attributed to him. It's not correct. Is an atom physical? Right. Why?
Because it's changeable?
Because it's changeable. Right? Physical means changeable, means material. They all mean exactly the same thing. Is plana physical? It's changeable. Yes. How does the plana, what are some of the ways in which plana can change? Well, yeah, I could squeeze the plana out from between my hands. Light can pass through it. We can have gravitational fields. The fields can change inside the plana. These are properties of the plana, so its properties can change. So is plana material? Yes, again. Material, physical, changeable, all mean the same thing. Exactly the same thing. There's no distinction. What are the three parts of the hydrogen atom?
Electron, proton, and planet.
You want to pick another one? I just did number 12 there because it was right after number 11. You want to look for another one?
Number 14.
What are the three things about quantum mechanics that we concluded at the end of chapter 1 we must keep in mind? Is it stated? Yes,
It's an ensemble theory.
that's one of them.
Statistical ensemble guiding wave. Empiriometric method.
Now that's the next question about two different ways of thinking that we use in physics generally. So it's on page 37, 38. There's a guiding wave structure. And the wave function reveals statistically something about the nature of the guiding wave interacting with the particle. Number two is that the guiding wave introduces the possibility of interference and quantization. And then number three is that quantum mechanics does not deal with individual particles, but with ensembles. All right, what are the general two ways of thinking? That's page 38. Generally, two ways of thinking in physics.
Realistically and empirically.
Empiriometrically is one. The other one is, well, realistically, but really is talking about physically, right? Because that's how we think. That's how our minds work. We learn about the physical world and we express things in terms of what we understand about the physical world. Even our language is based on that common understanding of the world. The meaning of words comes from physics, from the natures of physical things. Okay, so that's the two ways of thinking about physics, not just the empiriometric, but also just understanding physically what's going on. Okay, another one?
Might as well do 13.
Might as well, all right. Write the de Broglie relation and identify the parts. Say again?
H equals lambda over, I want to say mu, but that's not right.
That's not right yet. I don't think, depending on how you finish it, I guess. So what does the de Broglie relation relate? What to what? It's a relationship between two things.
Wavelength and the frequency?
That the wavelength, yes, but not the frequency. The momentum. The momentum of the electron, momentum of the particle, and the wavelength, but electrons don't have waves, they're not waves. They're associated with a guiding wave, so this is the wavelength of the guiding wave that's moving the particle, relating to the particle that's moving at this momentum. So that's what the de Broglie relation relates. You can write it another way in terms of wave number. So how does the wave number relate to the wavelength?
Reduce Planck's constant.
Is it 2 pi or lambda?
It's like a spatial frequency. Remember, in time, we have the frequency is related to the period. If we have a periodic motion with some period t, then we have a frequency, angular frequency, which is 2 pi over the period. And this is a kind of analogous relation. So he calls it a spatial frequency. K, the wave number is like a spatial frequency. Okay. What else? How about number 16? In the double slit experiment, we're shooting a beam of electrons at the double slit, and we observe an interference pattern on the other side. Okay, well, first remember, how does that interference pattern show up? If I shoot one electron at a time, what happens on the screen? What do you see on the screen? Just one electron goes through. Just get one blip on the screen. And it's not until you shoot a bunch of electrons that you accumulate the histogram of those blips that you can see the interference pattern. You don't see it with just one electron. Okay, is it right to conclude that the electron goes through both slits? No. What goes through both slits? The guiding. The particle can't. The particle can't do that. That's part of the confusion about the so-called wave-particle duality. Proper understanding of wave-particle duality is that there is both a particle and a wave. The particle is not a wave, and the wave is not a particle. So there's two entities involved. They have qualitatively different natures. What else? Got the canard uncertainty principle down? Can you explain that? You want to try, Mr. Rutland?
The Canard uncertainty principle is, you take an ensemble of similar prepared,
Not similar, identically.
identically prepared, I want to say part, that's silly. A system, if you take an ensemble of identically prepared, ensemble of identically prepared systems, yeah, there you go. Then you can, for example, split it into two sub-ensembles. One of the sub-ensembles makes one measurement of the momentum, and then they make a histogram of that. And the other ensemble, the other sub-ensemble, he makes one measurement of the position. It makes a histogram of that
One measurement for each system.
for each system within the
Each member
within
of
the
the
sub-ensemble.
Yeah.
It makes a histogram of the position. It makes a histogram that he finds the standard deviation of both, because standard deviation of the position and the momentum and the relationship between each other will be sigma x sigma p is greater than or equal to h bar over 2.
See all the essential ingredients there. You have one ensemble with all the members are prepared in the same way. And then you just do a division of that at random, take half and half. Make measurements of X on one, measure P on the other. And get standard deviation, all these different measurements of X may be different from each other, have some spread. All the people report back the results and we accumulate the results, there may be some spread. The same is true for P. So there's a standard deviation. The product of the standard deviations has a 4. H bar. Yes, ma'am.
Can you do, 32 with specifically E and F?
Say again?
32 with specifically E and F.
Okay. Okay. I think it doesn't actually ask for you to solve for the coefficients. Okay, so this is a barrier problem. It's different than the one I did at the beginning of class because there's combines a step up and a step down. So there's a region in a middle region of length A. Okay, a variation on this problem. Do that. Step down. And I think now you should not be surprised to find that there's reflection in this case. Transmission is not 100%. Okay. You should be able to handle a variation like that. If I gave you a problem with a step down. So a negative barrier does reflect. It's strange, but it does. Okay, so we have 3 regions. And in region 1, we have an incoming energy. Does it say the energy is less than the barrier height? Okay, so there's going to be real exponentials in this region. The energy is less than potential. So in region 1, there's the wave number is the same as region 3. Those have the same wave number. In region 2, we have a K constant. I'll write it as capital K. That looks like that. Okay, so the wave function the incoming wave, the reflected part. In region 2, we have 2 terms. Both terms are allowed. Because we don't have an infinite region here. So the wave function doesn't blow up inside this region. We threw it out when we did the barrier with just the step up. We threw out one of the exponentials because it would grow exponentially that way, but that's not true anymore. So in region 2, we have both terms. In region 3, then, we have just the right traveling wave. There's nothing over to the right that will reflect. We have only the right travel. Okay, so far, and this E is not the energy, so I'm trying to write it with some kind of make it different notation. But what we're going to want to solve for is E and B. These are kind of incidental, right? But if we're interested in the reflection and transmission, we'll get the reflection from this and the transmission from this. But these are part of the unknowns. Unknowns are B, C, D, and then a strict E. It's got 4 unknowns. Okay, so how many equations do we have? Okay, so this is part E, right up continuity. So the wave function is continuous. Right, which means that it has to be continuous at the interface between 1 and 2, and also continuous across the interface between 2 and 3. And also the first derivative. So we have 2 equations at each interface. Yes, ma'am.
Should that be, I don't know if I just can't see it. Is that psi 2 of A equals psi 3 then?
Yeah.
And same for the first derivatives?
Yeah.
Okay, cool. Sorry, I just.
Does that make sense?
Yeah.
Okay. So let's go ahead and evaluate this. This will be A plus B is equal to C plus D. The derivative then will be I K1 minus D. Kappa, let's see, that's right, C minus D. Right, that makes sense? And let's do the, oh, excuse me. Oh, I did the wrong one. That's here. I K1 minus D. Okay, now it gets a little more complicated when we're evaluating the functions at the second interface. And then the derivative is K is K1. Missing here. So I've done something wrong.
What about the E term?
I'm doing this, excuse me. I'm so sorry. Oh, we're just gonna let me write all this stuff down, all this nonsense. Between 2 and 3 is these two. Between 2 and 3, there we go. Okay, C e to the K plus B to the minus K is equal to E and E to the I K. There we go. Sorry.
So then is it not A plus B equals C plus D, but instead C plus D equals E?
You're looking at this one?
Yeah.
If we set x equal to 0 here, we just get A plus B. If we set x equal to 0 here, we get C plus B.
So I don't understand your process for the next line then.
C plus D equals E then.
I think I see the confusion here. See the second line, how it's psi region 2 of A.
Yeah.
He's He's going from the left to right, he's not working from.
Set x equal to a here. And so that's c e to the ka plus b e to the minus ka. And then we got to set x equal to a here as well. So this e to the I k1a. That's right. So let's look at the wave function here. These are functions of x.
Okay, I understand now.
Okay.
So to clarify, for the first one, since psi 1 and 2 are evaluated at 0, the exponents cancel
The exponents evaluate to 1.
to 1, so they're like not necessary in the second one, they are evaluated
That's right.
at x. Okay,
But at the second interface, they don't evaluate to 1. The exponent itself.
okay.
Okay, and then this last one here is going to be capital C e to the ka minus b e to the minus ka. 1 e. Okay, how many equations do we have? 4 equations, 2 for each interface. And how many unknowns do we have? 4 unknowns. So in principle, you would solve these 4 equations for the 4 unknowns, B, C, D, and E. The ones that we're really interested in are B and E. Unless you're wanting to know something about what happens in these tunneling regions. Okay, so then it's just linear algebra. Now it's messy. This is too much. I wouldn't give a problem to go beyond this, but I do. So you write out these equations, but not solve them. And the reflection coefficient is d over a. Whatever you solve for b here, divided by a, and reflection probabilities. And the transmission is going to be the strip e over a, and the transmission probability. Square of that, and we will find that those two add up to 1 in this problem. Right, mess you up too much, Miss Hoffman? You okay?
I'm just gonna have to go back to that on my own later.
Okay. All right. Just set, basically, you're just setting x to either 0 or a. You get 2 equations here and I get 2 equations here. And I messed it up when I did it the first time. I apologize for that. Okay. So no class Friday. I'll see you Tuesday morning and email me if you have questions. I'll be available.